Hello everyone, I am Runs Fan from Beihang University, Beijing, China. Our paper is Motion Hierarchical Gaussian for Dynamic Control in VR. This work is together with Lily Wang, Jian Wu, Qixiang Ma, Zhikai Wan from Beihang University. 3D Gaussian splatting. Splatting represents scenes as a set of Gaussian ellipsoids and has attracted significant attention in the field of virtual reality for its high rendering quality and real-time performance. Due to the explicit nature of 3DGS, simply scene geometry editing, such as object rotation and translation, can already be handled effectively. However, achieving precise and complex dynamic interactions remains highly challenging. Naively manipulating the motion of dynamic Gaussians often leads to erroneous and unnatural results, such as the robot is falling apart. Bernhard in 2023 proposed the 3D Gaussian splatting method, which has become a prominent technique in computer graphics. Yang in 2024 extended static 3DGS to dynamic scenes by constructing a deformation field for all Gaussians. Wang in 2025 introduced foveated rendering into 3DGS to further improve the rendering performance for dynamic scenes. Expect to simple Gaussian geometry editing. Multiple methods have been proposed to enable Gaussian deformation editing. Huang in 2024 combined Gaussians with control points, which achieves the control of the motion of the dynamic Gaussians. However, the number of these control points is relatively large for VR. Zhang in 2024 used the mesh-based XPBD simulation to drive Gaussian deformation. Luo in 2025 applied a grid-based MPM simulation and deformed Gaussians based on the simulated grid velocities. However, the pipelines of these simulation methods are relatively complex, and the Gaussian deformation is edited indirectly. To enable real-time intuitive motion control in VR, two challenges must be addressed. The first one is unstructured global motion representation. Global motion representations modeled by the deformation field lack hierarchical structure, making fine-grained motion control difficult and unintuitive. The second one is redundant motion learning. Learning independent motion parameters for each Gaussian leads to redundancy when modeling rigid or quasi-rigid objects.
We propose the motion hierarchical Gaussian representation to address above challenges. This representation is a tree-structured motion hierarchy. Each node of this representation contains Gaussian group with the same or similar local motion and the corresponding local motion. The local motion is defined as the rotation R, rotation center P, and translation T. Edge represents the local motion relationship between nodes of different layers. There are three types of the edge: unconstrained edge, rigid constraint edge, and non-rigid constraint edge. The motion hierarchical Gaussian is constructed with three steps. Step 1 is semantic and deformation-based initialization. Step 2 is motion hierarchical decomposition. Step 3 is local motion analysis-based refinement. In Step 1, we first reconstruct initial dynamic Gaussian with input monocular images. Then we use a top-down recursive clustering strategy to initialize the nodes based on the deformation and semantic information. Next, the edges are initialized via deformation similarity analysis by calculating positional similarity and rotational similarity. In Step 2, we compute the local motion of each node by decomposing the global motion based on the initialized hierarchical motion tree. For each edge type, we propose one kind of motion network to decompose the global motion into local motion. The unconstrained motion network directly predicts all three local motion parameters. The rigid motion network predicts local rotation, translation, and rotation center in canonical space. The non-rigid network predicts not only local rotation, translation, rotation center, but also center perturbation. To ensure structured and coherent motion decomposition, we introduced three spatial temporal regularization terms. The geometry consistency term is introduced to constrain the rotation center of rigid and non-rigid nodes. The temporal consistency term is introduced to minimizes the intranode variance of predicted local motion parameters. The hierarchical orthogonality term is introduced to encourages a more compact motion hierarchy by reducing the number of layers. The motion networks are optimized with RGB reconstruction loss and these regularization terms. The local motion of each Gaussian in each node is predicted by these motion networks. In step 3, we introduced a local motion analysis-based refinement method to address inaccuracies in the nodes and edges. This method consists of two parts: node refinement and edge refinement. In node refinement, we merge over-clustered nodes, remove over-small nodes, split under-clustered nodes, and reassign wrong-clustered Gaussians. In edge refinement, we reassign the edge types by assessing the spatial and temporal freedom and the axial instability. In experiment, we first compare our method with 5 SOTA methods on reconstruction quality with respect to time interpolation. Compared with them, our results has clearer detail and achieves high-precision motion reconstruction, such as the hands. In TREX scene, our method also achieves higher reconstruction quality compared to previous methods, such as the head. In LEGO scene, compared to previous methods, our method preserves sharper details such as the bucket. In robotic scene, our method also achieves superior reconstruction quality, such as the robotic arm.
We also compare our method with previous SOTA methods on segmentation quality with respect to time interpolation. Compared with them, our method demonstrates higher quality, reduce both over and under segmentation, resulting in more accurate and reliable segmentation. Based on the motion hierarchical Gaussian, we define 5 operations to enable flexible, intuitive motion control in VR. Motion node selection operation is used to choose a specific node to control. Freezing local motion operation is used to freeze local motion of a node without affecting the local motion of other nodes. Temporal control operation is used to decouple local motion from the global timeline, adjust the speed, enable asynchronous movement. Offsetting local motion operation is used to adding offsets to local motion to shift the motion trajectory, control displacements. Scaling motion magnitude operation is used to amplify or attenuate motion while maintaining physical plausibility. We compare our method with existing 4D Gaussian splatting approaches capable of motion control with motion fidelity as criterion. Although these methods allow limited motion editing, they each suffer from notable drawbacks. The original motion sequence is shown in the lower left. Control point method like SCGS require adjusting many control points. Modifying only a few points produces coarse and infeasible effect. Global motion methods like DGS produce unrealistic results in editing due to directly manipulating the global motion. Simulation-based methods like VRGS need complex precise parameters and small parameter change in editing results unplausible results. Motion-based methods like HiMOR require tunes complex non-intuitive weights. Naive tuning produces strange results. Compared with them, our method avoids these issues, requires no complicated process or intuitive tuning, achieving novel and realistic motion effect with high fidelity using just a few controls in editing. We also demonstrate the motion control process in VR. Before the motion control process, the initial motion errors cause the robotic system failure. User correct the motion errors through our motion control method. After the motion control process, the error is corrected and the robotic system is normal. In conclusion, we propose a motion hierarchical Gaussian-based dynamic control method in VR. We introduce a motion hierarchical Gaussian representation for monocular dynamic scene reconstruction. We propose a semantic and deformation-based clustering method to initialize the motion hierarchical Gaussian. We introduce a consistency and orthogonality regularization-based motion hierarchical decomposition method to generate the local motion. We propose a local motion analysis-based refinement method to optimize the nodes, edges, and local motion. Our method has several limitations. The first limitation is that we assume the clustered Gaussian groups and motion relationship are time consistent. The second limitation is that our method are only suitable for rigid or near rigid motions and cannot handle continuous motions. In future, we intend to introduce temporally dynamic segmentation prosperities and adaptive cluster strategy, and we intend to extend motion formulation, introduce new representations, and regularization. That's all. Thank you.